Welcome to Module 1, Foundations of Artificial Intelligence. In this opening module, we begin with the basic question that sits underneath every later technical, organizational, and ethical discussion in this course. What do we mean when we say that a system is intelligent? That question may sound simple at first, but it quickly becomes more precise once we separate ordinary software from systems that appear to reason, perceive, learn, adapt, or make decisions in ways that resemble aspects of human intelligence. Artificial intelligence is not a single tool or one narrow technique. It is a broad field concerned with designing systems that can perform tasks requiring some form of intelligent behavior. For that reason, this module is meant to give you a careful vocabulary before we move into specific methods, models, and applications. If the vocabulary is clear at the beginning, then the later topics become much easier to evaluate with academic precision, and it gives us the intellectual map for the course. We will approach artificial intelligence as both a technical field and a major force shaping contemporary society. At the technical level, AI includes ideas about representation, search, learning, reasoning, perception, and decision making, and those ideas give us a framework for understanding how intelligent systems are built. At the societal level, AI matters because it is now embedded in business processes, healthcare workflows, financial systems, transportation networks, educational technologies, security tools, entertainment platforms, and many other domains where decisions have real consequences. This dual perspective is important because AI is never only about algorithms operating in isolation. The value of an AI system depends on the problem it is meant to solve, the data it uses, the environment where it operates, and the human decisions that guide its design and deployment. Throughout this module, we will keep those connections in view so that artificial intelligence is understood as a discipline with both computational structure and human impact. One of the first distinctions we will develop is the relationship between artificial intelligence, machine learning, and deep learning. These terms are often used interchangeably in everyday conversation, but they do not mean the same thing, and confusing them can lead to weak analysis. Artificial intelligence is the broadest category, focused on creating systems that exhibit intelligent behavior. Machine learning is one important area within AI, where systems improve their performance by identifying patterns in data, rather than relying only on hand-coded rules. Deep learning is a more specialized area within machine learning, using layered neural network architectures to model complex patterns such as images, speech, language, and other high-dimensional data. By placing these concepts in the proper relationship, we can talk about AI more accurately and avoid treating every intelligent system as if it works in the same way. We will also look briefly at the historical development of the field, because the present state of AI makes more sense when viewed as the result of several waves of progress. Early AI research was strongly shaped by symbolic approaches, where intelligence was often modeled through logic, rules, and explicit representations of knowledge. Later advances were made possible by increased computing power, larger datasets, and improved algorithms, which allowed systems to move beyond narrow demonstrations and into practical applications at scale. This history matters because AI has never developed in a straight line. Periods of optimism, disappointment, renewed investment, and technical breakthrough have all shaped the field. Understanding that history helps us avoid both exaggerated fear and exaggerated hype, because we can see AI as a powerful but evolving discipline whose capabilities depend on scientific, engineering, economic, and social conditions. Finally, this module prepares us to analyze what makes an intelligent system different from traditional software. Traditional software is usually designed around predefined instructions, where the system follows explicit steps created by programmers. Intelligent systems, by contrast, are designed to simulate or extend capabilities such as reasoning, perception, learning, and decision making, which means they may respond to complex inputs in ways that are less rigid and more adaptive. That difference is one reason AI has become strategically important for organizations and governments, but it's also why AI raises challenging questions about reliability, accountability, bias, transparency, and responsible use. As we move through the course, we'll return to these questions repeatedly. For now, the goal is to build the conceptual foundation needed to study artificial intelligence carefully, critically, and professionally. We begin by defining artificial intelligence as a field of study concerned with creating systems that can perform tasks associated with intelligent behavior. That definition is intentionally broad because AI is not limited to one algorithm, one programming language, or one type of application. It includes the effort to build systems that can reason through problems, interpret information from the world, learn from experience, and support decisions under changing conditions. In traditional computing, we often expect a program to follow a fixed sequence of instructions, producing a predictable result when the same input is provided. Artificial intelligence expands that picture by asking how a system can act in ways that seem more flexible, more responsive, and more capable of handling complexity. That is why AI is best understood not as a single product, but as a technological discipline that continues to evolve as computing power, data, and methods improve. The scope of artificial intelligence becomes clearer when we look at the human capacities it tries to simulate or extend. Reasoning refers to the ability to work through relationships, rules, evidence, and goals in order to reach a conclusion or choose a course of action. Perception refers to the ability to interpret inputs such as images, speech, text, sensor data, or patterns in an environment. Learning refers to the capacity of a system to improve its performance by using experience or data rather than relying only on instructions written in advance. Decision making brings these abilities together because an intelligent system often has to evaluate information, compare alternatives, and produce an action or recommendation. AI does not need to copy the human mind perfectly to be useful. In many cases, it extends specific aspects of intelligence so that people and organizations can process information at a scale that would otherwise be impossible. This is also where the distinction between artificial intelligence and traditional software becomes important. Traditional software can be extremely powerful, but its behavior is usually tied closely to predefined logic. A payroll system, for example, can calculate wages accurately because its rules are specified in advance, while a scheduling program can follow constraints that a programmer has explicitly defined. An AI system may still include ordinary software components, but the intelligent part of the system is designed to operate with greater adaptability. It may classify new cases, detect patterns that were not manually listed, estimate future outcomes, or choose actions based on incomplete information. Because of that, the behavior of AI systems often requires a different kind of evaluation. We need to ask not only whether the program runs, but whether its judgments are accurate, reliable, explainable, and appropriate for the context in which it is used. The phrase intelligent behavior should therefore be treated carefully. It does not mean that the system has consciousness, personal understanding, or human intentions. In an academic and professional context, intelligence in AI usually refers to observable capabilities. The system can solve a problem, adapt to information, recognize a pattern, make a prediction, or support a decision in a way that would normally require some level of human cognitive effort. This distinction helps us avoid exaggerating what AI is while still recognizing why it is so significant. A system that can identify disease patterns in medical images, recommend financial risk categories, translate language, or guide a robot through a physical space may not understand the world as a person does, but it can still perform specialized intelligent functions. The practical power of AI comes from that combination: limited forms of intelligence embedded into systems that can operate quickly, consistently, and at large scale. Establishing this definition gives us the foundation for the topics that follow in the course. Intelligent agents build on the idea that a system can perceive an environment and act toward a goal. Knowledge representation examines how information about the world can be structured so that a machine can use it for reasoning. Machine learning develops methods that allow systems to identify patterns and improve performance from data. AI ethics asks how these systems should be designed, governed, and evaluated when their decisions affect people, institutions, and society. Future trends then require us to connect all of these ideas, because the direction of AI will depend not only on technical progress, but also on how responsibly these capabilities are used. By beginning with the definition and scope of AI, we create a disciplined starting point for studying both the promise and the limits of intelligent systems in modern life and professional practice as we go forward. In this slide, we shift from defining artificial intelligence to understanding how the field developed over time. That historical view matters because AI did not appear suddenly as a modern invention. It grew out of earlier questions about logic, computation, language, problem solving, and whether machines could perform tasks associated with intelligence. In the early stages, many researchers approach intelligence through symbolic methods, meaning they try to represent knowledge explicitly through rules, symbols, and logical relationships. This approach made sense for the computing environment of the time because computers were limited in speed and memory, and researchers often focused on problems that could be described in formal terms. When a system could solve a puzzle, prove a theorem, or follow a chain of logical rules, it seemed to show that some aspects of intelligence could be modeled computationally. Those early systems were important because they gave AI its first research identity, even though they were more limited than the systems we use today. Symbolic AI also shaped the way people imagined intelligent machines. The basic assumption was that if human reasoning could be broken into formal steps, then a machine could manipulate those steps and arrive at intelligent conclusions. That idea produced important work in expert systems, knowledge bases, search algorithms, and rule-based decision making. In an expert system, for example, human knowledge from a specialized field could be encoded as rules that a program would apply to new cases. This was a major milestone because it showed that AI could move beyond laboratory demonstrations and support real decision processes in areas such as diagnosis, planning, and technical troubleshooting. At the same time, symbolic systems also reveal a serious limitation. The real world is messy, ambiguous, incomplete, and constantly changing, and it is difficult to capture all of that complexity in explicit rules written by human experts. The later growth of AI was driven by a combination of increased computing power, greater data availability, and algorithmic improvements. These three forces changed what AI systems could realistically do. More computing power allowed researchers and organizations to train larger models, process complex information, and experiment with methods that would have been impractical in earlier decades. Greater data availability gave learning systems the raw material they needed to identify patterns, because many modern AI methods depend on examples rather than manually specified rules. Algorithmic improvements then provided more effective ways to search, optimize, classify, predict, and learn from those examples. When these forces came together, AI began to accelerate, and the field moved from relatively narrow symbolic programs towards systems that could handle images, language, speech, recommendations, forecasting, and other tasks with practical value. This historical pattern helps explain why artificial intelligence has developed in waves rather than in one smooth progression. There have been periods of enthusiasm, disappointment, and renewed progress when technical conditions improved. Early AI showed that machines could perform formal reasoning tasks, but it struggled when knowledge had to be flexible, uncertain, or learned from experience. Later methods, especially those connected to machine learning, became more powerful as data and computing resources expanded. That does not mean symbolic approaches disappeared or became irrelevant. Instead, the field became broader, combining multiple traditions and methods depending on the problem being addressed. A modern intelligence system may include rule-based components, statistical models, learned representations, optimization methods, and human oversight, all working together within a larger application. The practical result is that AI plays a major role across business, science, government, and everyday life. In business, AI can support forecasting, customer analysis, process automation, fraud detection, and strategic decision making. In science, AI helps researchers analyze large data sets, identify patterns, simulate complex systems, and accelerate discovery. In government, AI may be used for public service delivery, cybersecurity, transportation planning, document analysis, and resource allocation. But these uses must be evaluated carefully because public decisions affect citizens directly. In everyday life, AI appears in search engines, recommendation systems, language tools, navigation systems, mobile assistants, spam filters, and many other technologies that people use without always labeling them as AI. So the historical evolution of artificial intelligence is not just a story about better machines. It is a story about how advances in symbolic reasoning, computing power, data, and algorithms turned AI into a practical force embedded in modern society. Okay? In this part of the module, we clarify one of the most important vocabulary distinctions in AI, the relationship among artificial intelligence, machine learning, and deep learning. These terms are connected, but they are not interchangeable, and using them carefully helps us think more clearly about what a system is doing. Artificial intelligence is the broadest concept because it refers to the larger field focused on creating systems that exhibit intelligent behavior. Within that field, machine learning represents a major approach in which systems improve performance by finding patterns in data. Deep learning sits inside machine learning as a specialized family of methods that uses layered neural network structures to learn complex representations. Once we understand this hierarchy, we can describe AI systems with greater precision instead of treating every intelligent technology as if it were built the same way. Artificial intelligence includes approaches that do not necessarily depend on machine learning. A system may use rules, logic, search procedures, planning methods, knowledge representation, optimization, or combinations of techniques in order to behave intelligently. For example, an AI system designed to plan a route, schedule tasks, or reason over a structured knowledge base may rely on explicit representations and decision procedures rather than learning from large data sets. That point matters because AI is defined by the goal of producing intelligent behavior, not by one specific method for producing it. Machine learning is important in contemporary AI, but it is still one component within the wider discipline. When we say that AI is the broad field, we are recognizing that intelligence can be modeled through multiple computational strategies, depending on the problem, the environment, and the decision the system must support. Machine learning narrows the focus by emphasizing systems that learn from data. Instead of writing every rule by hand, developers provide examples, observations, or historical records, and the learning algorithm identifies patterns that can be used to classify, predict, recommend, cluster, or detect anomalies. This is why machine learning became central to modern AI. Many real-world problems are too complex or too variable to solve only with manually written instructions. A spam filter, a churn predictor, or an image classifier may improve by being trained on examples, then tested on new cases. The system is not learning in the human sense of personal understanding, but it is adjusting its internal structure so that its outputs become more useful according to a defined performance goal. That is the practical meaning of learning in machine learning. And it explains why data quality, model evaluation, and context are so important. Deep learning is a specialized area within machine learning, and its importance comes from the way it represents patterns through layers. A deep learning model uses neural network architectures with multiple layers that transform input data into increasingly abstract representations. In image analysis, lower layers may respond to simple visual features, while later layers may capture more complex structures that help the model recognize objects. In language processing, layered models can represent relationships among words, phrases, meanings, and context in ways that support translation, summarization, question answering, or text generation. The word deep does not mean that the system understands deeply in a human philosophical sense. It refers to architecture and the multiple stages of representation learned from data. This distinction matters because deep learning has produced impressive AI capabilities, but it is still one method within machine learning, which itself remains one part of artificial intelligence. These distinctions give us precise academic vocabulary, and that precision changes how we evaluate technology. When an organization says it is using AI, we should ask what kind of AI it is using, whether it involves machine learning, whether it uses deep learning, what data shape the system, and what intelligent behavior it is expected to produce. A rule-based decision system, a supervised learning model, and a deep neural network may all belong somewhere within the AI landscape, but they raise different questions about design, performance, explanation, reliability, and governance. This vocabulary prepares us for later topics because the course builds on this conceptual map. If we confuse the categories, we weaken our analysis. If we distinguish them carefully, we can discuss AI systems with the discipline expected in graduate level work. So the main lesson is that artificial intelligence names the broad field. Machine learning names a data-driven component within that field. And deep learning names a specialized machine learning approach central to many modern intelligence systems. Artificial intelligence becomes easier to understand when we connect it to the domains where it is already being applied. Its value is not limited to abstract computation or laboratory research. It appears when intelligence systems help people and organizations interpret information, automate tasks, improve decisions, and respond to complexity at scale. Across industries, the same general pattern appears in different forms. A system receives data from an environment, identifies meaningful patterns, and supports an action or recommendation. That action may involve diagnosing a condition, detecting fraud, guiding transportation, personalizing instruction, coordinating a robot, monitoring a security threat, or recommending entertainment content. What changes from one domain to another is the nature of the data, the risk involved, the performance requirements, and the human responsibilities surrounding the system. In healthcare, AI is often used to support clinical decision making, image analysis, risk prediction, patient monitoring, and administrative efficiency. A model that analyzes medical images may help detect patterns that are difficult to notice quickly, while a predictive system may identify patients who are at a higher risk for complications or readmission. These applications can create value by helping clinicians manage large volumes of information, but they also require careful oversight because health decisions affect human well-being directly. An AI system in healthcare cannot be judged only by technical accuracy. It must also be evaluated for fairness, reliability, explainability, privacy, and fit within clinical practice. This is why healthcare shows both the promise and the responsibility of intelligent systems. The technology can extend a professional judgment, but it should not be treated as a replacement for ethical and accountable human decision making. In finance, AI supports fraud detection, credit risk analysis, customer service automation, forecasting, and compliance monitoring. Financial environments generate large volumes of data, and AI systems can identify unusual behavior, estimate risk, or recognize patterns faster than manual review alone. A fraud detection system may compare a transaction against prior behavior and broader patterns to determine whether it appears suspicious. At the same time, finance illustrates why AI must be handled carefully because decisions about lending, pricing, access, and risk can affect people's opportunities and economic stability. If the data reflects historical bias or incomplete information, the system may reinforce unfair outcomes while appearing mathematically objective. So in finance, AI creates strategic value by improving speed and scale, but it also demands governance and validation and accountability. Transportation, robotics, and security show how AI can operate in environments where sensing, timing, and action are especially important. In transportation, AI may support route optimization, traffic prediction, logistics planning, driver assistance, and autonomous mobility, all of which require systems to process changing conditions and make timely decisions. In robotics, AI connects perception with physical action, allowing machines to navigate spaces, manipulate objects, inspect equipment, assist workers, or perform repetitive tasks with increasing flexibility. Security applications may involve anomaly detection, threat monitoring, identity verification, malware analysis, or video analytics, where the goal is to identify signals that indicate risk. These domains remind us that AI is often part of a larger socio-technical system. The model is only one component. Sensors, infrastructure, human operators, policies, and safety requirements all shape whether the application is effective and responsible. Education and entertainment demonstrate another major pattern. AI can personalize, recommend, generate, and adapt content for individual users. In education, intelligent systems may support tutoring, feedback, assessment, accessibility, learning analytics, and adaptive practice, helping instructors and learners identify where more support is needed. In entertainment, AI appears in recommendation, systems and content generation, game behavior, media production, search, and audience analysis. A recommendation engine may seem simple from the user's perspective, but behind it is a system that uses patterns in behavior, similarity, context, and preference to decide what content should appear next. Across all of these domains, AI supports decision making by helping organizations interpret complex information, and it supports automation by allowing systems to perform tasks that previously required human attention. Identifying AI domains is more than listing industries. It is the first step toward analyzing how intelligent systems create value, change professional work, and reshape responsibilities across organizations and society. Intelligent systems are different from traditional software because they are designed to do more than execute a fixed sequence of predefined instructions. Traditional software can be reliable and powerful, but it usually behaves according to rules that developers specify in advance. If the input matches the condition, the program follows the program path and produces the expected result. That model works well for tasks where the problem is stable, the rules are clear, and the range of possible situations can be described ahead of time. Artificial intelligence becomes important when the environment is more complex than that. Because intelligent systems are designed to simulate or extend abilities such as reasoning, perception, learning, and decision making. Those abilities allow the system to respond to information in ways that are more adaptive than ordinary rule execution. Reasoning is one of the first characteristics that helps distinguish intelligent systems from traditional software. In an AI context, reasoning means that a system can use information, relationships, constraints, or learned patterns to reach a conclusion or support a decision. That reasoning may be based on explicit logic, statistical inference, probability, optimization, or some combination of methods, depending on the system being designed. A traditional program can follow a rule such as, if this value exceeds a threshold, then trigger an alert. An intelligent system may evaluate several signals together, weigh uncertainty, compare alternatives, and estimate which outcome is most likely or useful. The difference is that intelligent systems are designed to operate where rigid instructions alone may not capture the full complexity of the problem. Perception is another central feature because many AI systems must interpret information from the world before they can act on it. That information may arrive as images, speech, written text, sensor readings, transaction histories, behavioral patterns, or environmental signals. Traditional software can process data when the data is structured in predictable formats, but perception-oriented AI is often asked to find meaning in inputs that are messy, incomplete, or high-dimensional. A computer vision system, for example, does not simply receive the word object as a clear instruction. It must analyze patterns of pixels and infer what those patterns represent. A language system must process words, context, and relationships among ideas. These capabilities matter because intelligence often begins with interpretation. Before a system can decide, recommend, classify, or act, it must first transform raw input into something meaningful enough to use. Learning adds another layer to this distinction. Traditional software normally changes only when developers revise the code, update the rules, or modify the database. Many intelligent systems, especially those built with machine learning, are designed so that performance can improve through exposure to data. The system identifies patterns in examples and uses those patterns to make predictions, classifications, recommendations, or judgments on new cases. This does not mean the system learns with human consciousness or personal understanding. It means that the system adjusts its internal model so that its outputs better align with a defined objective, such as reducing prediction error or improving classification accuracy. Learning is one reason AI can be powerful, but it is one reason AI requires careful evaluation. A system that learns from biased, incomplete, outdated, or poorly labeled data may produce outputs that appear intelligent while still being unreliable or unfair. Decision making brings reasoning, perception, and learning together in practical use. An intelligent system is often valuable because it can help select an action, recommend an option, rank alternatives, detect risk, or support a human decision maker. In organizations, this creates strategic importance because AI can process large volumes of information faster than people can manually review it, and it can identify patterns that may otherwise remain hidden. However, strategic importance does not mean automatic correctness, because AI systems may influence hiring, lending, medical prioritization, security monitoring, education, transportation, and other high-impact areas. Their decisions must be examined for accuracy, transparency, fairness, accountability, and alignment with human goals. This is why the difference between intelligent systems and traditional software is more than a technical distinction. It shapes how systems are designed, tested, governed, and trusted. As we move forward, this foundation will support later discussions of AI problem solving, machine learning, and ethics, because every responsible AI application begins with understanding what the system is capable of doing, what it cannot do, and what human responsibility must remain around it.